which the title is Diagonalization. So again, the philosophy is essentially once you know the eigenvalues of a matrix, you can simplify the matrix. And the question is, what do we mean by simplify? And essentially, the first definition tells you what we mean by simplification. So this in your book is definition 1 and 2. So the first thing is what we call a similar matrix. So if A and P are n by n matrices, P invertible, then we call A and P inverse times A times P similar. So the matrix A and this matrix, they are called similar, and P can be any invertible matrix you like. Then these two matrices are considered similar. And now the optimum is if A is an arbitrary matrix, but this matrix, which we call similar, is a diagonal matrix, because then it means A is similar to a diagonal matrix. And again, philosophy is diagonal matrices are easier to understand. So A is called diagonalizable. If there is a matrix P such that P inverse AP, which is similar to A, is actually a diagonal matrix. So only numbers along the diagonal. And so this is similar and diagonalizable if there is a similar matrix such that you have diagonal shape. The first question is, what in the world is this here now? No? And now it really goes back to chapter 4.6. 4.6, remember, we had basis transformation. We said something, oh, and also I think one of your homework, they gave you an invertible matrix and said, okay, what kind of basis transformation corresponds to this? So it turns out every invertible matrix is actually a basis transformation. So now you think about what are we actually doing here? We change the basis, apply A, and change the basis back, because P inverse is the inverse base change. So what this actually means, a matrix is considered similar if it's actually the same operation, but looked at it in a different coordinate system. Remember, base change, apply A, change base back. This is like, I think yesterday I explained in the office hour, a base change is like, for example, changing the currency. No? So what this means, for example, change from dollar to English pound. Do something in English pound, change back from pound to dollar. Yeah. So essentially you go to a different country, do something and come back. But what you do is actually the same thing. No? For example, the operation A might be buy Microsoft stocks. No? So you can buy the Microsoft stocks here, or you can go to England, buy Microsoft and transfer your money back, for example. So essentially this and this is the same operation, but looked at it in different coordinate systems. Yeah. So similar is actually even a weak term. It's actually even better. It's actually, what it says actually is this and this is the same operation, looked at it in different coordinate systems. Okay, and now then suddenly this also makes sense. So this is the matrix A looked at it in different coordinate systems. So what this means is if A is diagonalizable, it means if you find the right coordinate system, your matrix is just a diagonal matrix. Even it might not look like this, no? So in the right coordinate system, your matrix is a diagonal matrix. So this is what this says, which also means these are actually the eigenvalues of A. So again, this is a lot, but so the idea of this kind of change of a matrix is you change the coordinates to the coordinates which are given to a new basis, which are actually, turns out, the columns of P. Then you apply the matrix, and then you change your coordinates back. Yeah. Okay, and so this is why, if you have never seen this, is why in the world would be called similar. It turns out it's actually even better than similar. It's actually the same, just in a different coordinate system. Okay. So, and now I have a list of results about similar matrices. None of them is actually complicated to prove. I just like to write them down, and we can just shortly think about how we would, or what's behind that this equality actually holds true. Turns out A and this have the same determinant. So if a matrix is similar to another matrix, the two matrices have the same determinant. Again, because they are kind of the same thing anyway, that makes sense. But actually, to prove this, I only need to use the fact that determinant of a product is the product of the determinants, and the determinant of the inverse is 1 over the determinant of P. So that is really, it's just a one line with the results of chapter 2. Then next thing is A is invertible if and only if PA inverse P is invertible. Again, that's easy to see, because if A invertible is, product of invertible matrices is invertible. So that is actually also an easy result based on chapter 1 when we talked about product of invertible matrices is invertible. So again, I will not show it, but it's not difficult to show by just using results from chapter, I think it was 1.5 or so, when we talked about product of inverses. Then we have A and P inverse AP have the same rank. From all the properties which follow, this is a central property. And that's also a little bit, we have not actually done this, but we used it already yesterday when we talked about the connection between the rank of A and the rank of the reduced row echelon form, that we do reduced row echelon form to find the rank. And one argument which I told you, but we never have shown, if you have linear independent vectors, you multiply them by an invertible matrix, they stay linear independent. So that shows if, let's say, A has 5 linear independent columns, then you multiply by P inverse, they stay 5 independent columns. Now, what about the P on the right? That's actually the same thing, just instead of the column, it's for the rows. So if you have 5 independent rows, then AP also has 5 independent rows. So that's actually behind this. But again, it goes back to the fact that linear independence stays under multiplication by invertible matrices. Again, not difficult to show, but the book doesn't have it. So for this reason, I also skipped this, but that's behind if you ever like to find a proof for it. Then, because of the rank property, right away we also have that the dimension of the null space, which is called the nullity, is the same. Because nullity is just n minus the rank, but if the rank is the same, the nullity stays the same. So that is what you did in your homework, which I think you're working on in the moment. So this is really the important property. All the rest now follows quite simple, beside the next one, which is also not a big thing, but okay, I also will not prove it. This matrix and this matrix have the same trace. And the reason for this is actually, it turns out the trace is the second highest coefficient in the characteristic polynomial. And because the determinant is the same, the characteristic polynomial is the same. So, and the coefficient stays the same, that means the trace is the same. So again, something we have not done, but it's not so difficult to show. And so the next one is that A and P inverse AP have the same characteristic polynomial. Again, that follows from this here. Because what is the characteristic polynomial? You only write lambda I minus I here on both sides. No? And then you can pull out P here, and again, it cancels. So that is actually easy to show with a determinant. And again, because of what I told you, that also implies actually this one.
What does that say? The same polynomial?
Characteristic polynomial.
Oh, thank you. It's a little bit cut off on my screen.
Yeah, no, it's also my writing is, yeah. Okay, so I put it here. So I try to write better. Characteristic, okay, it's always too short. I have not enough space. Characteristic polynomial. Okay, and the zeros of the characteristic polynomials are the eigenvalues. That's what we just did before the break. So if the characteristic polynomials are the same, the eigenvalues have to be the same, okay? So A and P inverse AP have the same eigenvalues. That follows right away from this. And then finally, the eigenspaces also have the same dimension. That again follows from the rank property. So if A has, for example, two linear independent eigenvectors for the eigenvalue 5, then this also has two linear independent eigenvectors for the eigenvalue 5. But the eigenvectors might be different, but they're still two. Yeah, and for sure they're different because you look in a different coordinate system. No? So that includes the possibility that the eigenvectors look different, even they're the same vectors. Okay, and so this is a long list of things, but a lot of them are just nice to know. No? So if you have a matrix A and a matrix B, matrix A has determinant 5, matrix B has determinant 7. The question is, can they be similar? No, because if they are similar, the determinant has to be the same. No? Or you have one matrix A, another matrix B. Maybe the determinant is the same, but the characteristic polynomial is not the same. Then you also know they cannot be similar, which means they cannot be the same thing just by looking at a different coordinate system. Yeah. Okay. So in some sense, what's happening here? Remember, the coordinate system was already the attempt to make us independent from our Cartesian coordinate system, because the Cartesian coordinate system is not always the best one. We have to be independent of the coordinate system. So that was kind of section 4.6. It was, how do we change from one coordinate system to the next? And what we found out, every invertible matrix makes a coordinate change. So that's the idea. Now, essentially what's happening here, we apply this idea to matrices now. Because we like to know two matrices, are they maybe the same thing, just looking at them in a different way? That's the problem, and that's a very complex problem. Now you have essentially in 3 dimensions, for example, you have 9 numbers in a 3 by 3 matrix. No? And you have 9 numbers here, 9 numbers here, but maybe they're actually the same thing, also same thing in the sense that they transform the space in a similar way. Yeah. Okay, so, and this is actually what's behind this whole chapter, that we understand how to think about what does a matrix really do. And if two matrices are actually doing the same thing, they take, for example, one plane where they stretch and another vector where they shrink, where they either shrink or stay constant, and the other matrix does the same, oh, then we say, okay, then they're actually the same thing. No, just looked at it in different ways. Okay, so in some sense, it comes back to geometry here. What are matrices doing? And that's a preparation for it. And now we get two results. As I said, maybe that's also the end also for today already. So then all the calculations where we actually do this will be on Monday. So